To begin solving this problem, it's going to be useful to find the angle that the strings are making relative to this vertical rod. So we're going to call that angle theta. And to find that angle, we will note that the distance from here to here, as indicated in the diagram, is that 3 meters. But because of the symmetry of the arrangement, we can conclude that this distance here is 1.5 meters. And then the same thing is true with this distance right here, also 1.5 meters. And then what we'll do is draw a horizontal line from the midpoint of the rod to create a couple of right triangles. We can focus our attention on this right triangle, and perhaps we can even redraw it on the side of the figure. We have formed a right triangle whose hypotenuse is 2 meters and whose side adjacent to the desired angle is 1.5 meters. So a trigonometric ratio that involves the adjacent and hypotenuse sides of a right triangle is the cosine. We can say that the cosine of that angle is going to equal the adjacent side of 1.5 meters over the hypotenuse of 2 meters. We can then take the inverse cosine of both sides. So the angle would be the inverse cosine of 1.5 over 2. Which on a calculator set to degree mode turns out to be about 41.4 degrees. Now that's not any answer to the question, but that's a useful piece of information for us to know. In addition, we're going to need to know the radius of this circular path. You can see that this ball is traveling in a circular path. Later on, we're going to end up needing the radius. Now, from this picture, the radius of that circular path would be this horizontal segment right here. We can call that segment R, and we wish to find that. So coming back to the original triangle that we drew, we can call that R, and we can use another trigonometric ratio, or maybe even just use the Pythagorean theorem. Why don't we do the Pythagorean theorem? We can see that R squared plus 1.5 squared is going to equal 2 squared. We can simplify this a little bit here. Subtract the 2.25 from both sides of the equation. You get R squared is 1.75, and then take the square root to get R. We can see that the radius of the circular path is approximately 1.32 meters. So those are some data that we're going to be using in a few minutes. But for now, we want to take a careful look at the ball and draw a free body diagram. So here is a free body diagram showing forces acting on that ball. We have the downward gravitational force, and then we also have these two tension forces. We've got T1 pulling up and to the left on the ball, and then T2 is pulling down and to the left on the ball. And we've marked that angle theta, but let's just justify how we know that that theta is the same theta that we found earlier. So go back and look at the original diagram on the right side here. The theta that we found originally was this angle right here. We could even label that theta. And from geometry class, we know that the alternate interior angles of this arrangement are equal to one another. So in other words, this angle right here is theta. And then the same thing is true over here. We have the same angle marked theta here, and then the alternate interior angles, which would be this angle and that angle, are congruent. So this is also theta here. So that is how we justify the presence of those two thetas in our free body diagram. Now what we need to do is start summing the forces, and we're going to do that in the y direction first. And in order to accomplish that goal, we're going to need to break the forces up into their x and y components. So let's look at T1. We've got an y component pointing vertically this way. This is going to be T1y. That is actually adjacent to the angle, so we can represent that as T1 times the cosine of theta. And then this component here, this is the x component, that we're going to call T1 sine of theta. We're using sine because that component is opposite of the angle theta. And then similarly for T2, we have a y component pointing down. That's going to be T2 times the cosine of theta, and then we have an x component going to the left. That's going to be T2 times the sine of theta. Now focus your attention on the forces acting in the y direction. Let us call the upward direction positive and the downward direction negative. We have T1 times the cosine of theta pointing in the positive y direction. We also have T2 times the cosine theta pointing in the negative y direction. So we'll say minus T2 times cosine theta. And then it's a little bit hard to see, but there's also the downward gravitational force. It's this little vector right there. That's pointing in the negative y direction, so that's going to be minus mg. Now, of course, this ball is not accelerating in the vertical direction, so the sum of these forces would actually be equal to 0. Now, we're going to simplify this just a little bit. We're going to add the mg to both sides of the equation so that we can isolate the tension terms on one side. And then we're going to divide every term by cosine theta. And we'll see momentarily why this is going to be a good way of setting ourselves up here. So if you divide everything by cos of theta, the cos thetas cancel on the left side. So you have T1 minus T2 is equal to mg divided by the cosine of theta. That's an equation we're going to hold on to for a moment, but let us return to our free body diagram, and now we're going to start summing the forces in the x direction. Now, when we do that, you will notice that for our Newton's second law equation for the acceleration right here, we've added a subscript c to represent centripetal acceleration. Now, why would we do that? Well, recall that the ball is moving in a circular path. It's kind of hard to see in this drawing, but there's a circular path right here. The center of that circular path is right there in the diagram, and we know that in order for an object to move in a circular path, it needs a centripetal acceleration. It also needs a centripetal force. Now, the centripetal forces are going to be the forces that point towards the center. Very important concept. So this vector is pointing towards the center of the circle, and so is this vector pointing towards the center of the circle. None of the other vectors are. So when it comes to summing the forces in the x direction, we're going to take those two highlighted forces and we're going to add them together. We're going to have T1 sine theta plus T2 sine theta. And then on this side, we're going to have mass times centripetal acceleration. Now, centripetal acceleration, we all know, is v squared divided by the radius. So we'll make that substitution as well. And like before, we're going to divide every term by this trigonometric function here, in this case by the sine of theta. When you divide over here, that sine of theta is going to end up in the denominator. So those sine thetas cancel, and now we have T1 plus T2 is equal to mv squared, all divided by r sine theta. Now let's bring back in the other equation that we developed using the y direction information. Now we can begin to see the usefulness of our arrangement here, because we're going to actually add these equations together. And if you look carefully, the T2s are going to cancel because you're adding T2 to negative T2. T1 plus T1 is going to equal 2T1. And then over here, admittedly, it's a little bit messy. We're going to have mv squared over r sine theta plus mg over cosine of theta. So that would be our setup. We could actually solve for T1 by dividing both sides of this by 2. We get this rather hideous expression, but this will be useful to us. We can use it to solve for T1 by plugging in all of the known pieces of data. And if you carefully plug that into your calculator, you should find that T1 is approximately 109 newtons. So that is the correct answer for T1. We can go back and find T2 rather easily by selecting any one of these two equations here. Why don't we just grab this one and bring it down? We can subtract T1 from both sides. This gives us negative T2 is equal to mg over cos theta minus T1. And then basically just divide every term by negative 1. And you get negative mg over cos theta plus T1. Now we'll fill in the known values once again. And when you compute that, you should get T2 is approximately 56.4 newtons. This would be the correct answer for T2.